You're listening to the fifth episode of our TechTalk podcast, and I'm Dr. Khan. Winters have arrived, and the new variant is rolling around. Stay safe, folks, and have a diet that boosts your immunity. Let me see what I've got for you in today's episode. Oh yeah, it's about smart materials for biomedical engineering. Many of us underestimate the importance of smart approaches in our daily life. Smartness in context of humans is all about hard work combined with intelligence that leads you in right direction at right time. At work, you all have noticed some of us are smart enough to deceive others and some of us are smart enough to get quality work done on time. But that was on a lighter note. Recently, the climate change and depletion of natural reserves have made us consider a good green approach and embrace the beautiful concept of sustainability. Speaking of sustainability and eco-friendly industrial designs reminds me of Singapore. I love Singaporeans and their commitment to sustainable development goals. Their green buildings and NTO architecture are just so beautiful and you must visit it once. Clean and green approach beautifully implemented. Let's get back to smart materials. What are these? Are they even needed in biomedical engineering? Do humans also have climate change issues within their body? Yes, we do. We do suffer when the right materials are not chosen to design devices aimed to perform impaired physiological functions. Our focus today is on the smart materials for coronary stent and contact lens. So let's begin. Heart diseases are very common nowadays, and the coronary stenting is performed to open the blocked arteries of your heart. So what you do is you insert a metallic tube with meshwork inside your heart vessel and you expand it with the help of a balloon. The metallic tube that you insert inside your coronary vessel is called different meshwork geometry, and it's made of different materials. Dr. Kazaka from University of California when reported interventional issues with the use of slotted tube stents and sheath-protected delivery system. Dr. Kazaka says that the slotted tubes are bulky, inflexible stents, and it's very difficult to deploy them in tortuous vessels. I believe by tortuous he meant morphological features of the vessel. This study was reported in 1998 and published in International Journal of Catheterization and Cardiovascular Diagnosis. Sheath-protected delivery system were introduced to avoid stent immobilization following dislodgement from balloon. Dr. Kizaraka writes in his retrospective study, length and rigidity of reported stent limited its use in tortuous and calcified vessels. And basically they were unable to cross the lesion, so they changed the deployment method and used a bare metal stent, and they were hand crimped in complicated vessels. And they deployed manually bare metal stent in almost 170 patients out of 209. With this hand crimping stenting, complications were seen in 9 cases, and in 8 cases, successful deployment were performed. However, there was one deployment failure. Due to limitations arising from stent material and its dimensions, intervention was modified to perform stenting in challenging vessels. This method is risky, Dr. Kizaoka says, because unprotected stent can slide off balloon and can undergo immobilization. This study was more than 2 decades old and used here as a referral to help you understand the advancements that have taken place so far in the field of stent manufacturing. Now we are progressing towards a smart bioresorbable stents. And earlier, to get rid of the masqueraded by balloon expandable stents, for example, were expansion, vessel injury, dislodgement, and thrombosis, self-expanding stents were introduced, which are made of shape memory alloy, for example, nitinol. Nitinol is an alloy of nickel and titanium. For those who don't know what shape memory alloys are, these are the materials that change their intrinsic properties or should face a transformation with change in external stimuli, for example, thermomechanical. Stents was the first self-expandable stent made of nitinol, which underwent clinical trial and showed encouraging results. It takes days to a few weeks to reach its maximum diameter, and titanium and nitinol forms a thin layer of titanium oxide on the surface of the stent upon meeting biointerface. So this actually prevents leaching of nickel ions in the bioenvironment, which can later cause toxicity. Further research studies show that glow discharge, low temperature plasma treatment of nitinol-based stent can give good control over crystalline phase of titanium dioxide, which ultimately help in the prevention of platelet adherence that later cause thrombosis. Permanent stenting using coronary stent made of 316 stainless steel, cobalt, chromium, or nitinol, it can develop clinical conditions at later stages of life, for example, thrombosis, inflammation in stent restenosis, or vascular smooth muscle cell hyperplasia. Drug-eluting stents were introduced to curb the inflammatory response, but clinicians report that de novo new atherosclerosis remains a leading cause of late stent failure. To overcome these challenges, bioresorbable stents were introduced, which are made of metals like magnesium, zinc, and iron, and they can undergo biocorrosion after some time, and they're able to self-degrade. Iron, zinc, and magnesium ions are already present in high amount in human body, and chances of toxicity due to leached out ions, it's less. But there's a problem. Bioresorbable stents, they have mechanical properties which are compromised, and recalling you the parameters which qualify a material for stent manufacturing are high elastic modulus because it prevents recoiling of stent. A low yield strength is required so that expansion of the stent can be performed at low inflation pressure. So you don't want to use material which actually has high yield strength because it can damage arteries because you require a high pressure to expand stent. And you need high tensile strength so that you have increased radial strength after expansion, and this also facilitates use of thinner struts. Metal use should be very ductile so that a stent can undergo plastic deformation during expansion without any cracking. And I would like to highlight here a medical problem called restenosis, which is a major challenge following stent deployment. So what happens once you expand the stent, endothelial layer gets denuded, which initiates inflammatory response and cause a proliferation and migration of vascular smooth muscle cells. This ultimately reduces lumen diameter, and at times it can cause complete occlusion. Stents with protruding geometry and thicker struts worsen the condition called restenosis. So when you are designing a stent, you consider these parameters very carefully, and you have to be thoughtful that smooth muscle cells often proliferate around the stent struts that leads towards in-stent restenosis. And like I said earlier, drug-eluting stents were introduced to curb inflammatory response at first through the gradual release of drug. However, in all generations of bare metal and drug-eluting stents, there is persistent late failure due to late thrombosis and new atherosclerosis. Smart stents like those made of resorbable metals can eliminate late dislodgement issues or thrombosis or new atherosclerosis. Magnesium-based bioresorbable stents have already been clinically trialed, and An example is absorbable metallic stent introduced by Biotronic, a German company. Oliver mentions in his study that in cases where vessel diameter is very small, late lumen loss due to intimal hyperplasia can occur. So in such cases, metallic bioresorbable stent can be a very useful candidate. Absorbable metallic stent introduced by Biotronic. It has a strut diameter of almost 165 micron, and it has got 93% by weight magnesium in it. There is another absorbable metallic stent called Progress, which showed encouraging results in clinical trials. And it has also shown effective deployment, safe corrosion in coronary arteries after initial 4 months. Clinician says that mechanical integrity and slower corrosion rate should be considered in next generation of magnesium-based bioresorbable stent. And few other materials which researchers are considering for designing resorbable stents are iron and zinc. Iron-based bioresorbable stents, they are in clinical trial already. Now I will talk about smart contact lens. Glaucoma is the leading cause of irreversible blindness among people who are over 60, and it's a group of conditions that cause damage to optic nerve. For diagnosis, clinicians use intraocular pressure as an indicator of glaucoma. And IOP, intraocular pressure, is the pressure your aqueous humor exerts on anterior eye. A golden standard to measure IOP is Goldman applanation tonometry. Portable tonometer like Tonopen and iCare were initially introduced, but their usability is limited as it requires trained professional and patient can take his own IOP measurement. And there is this amazing product introduced by Sensimed-Co, a Swiss company, called Triggerfish Smart Contact Lens. It allows you to measure ocular volume for glaucoma management. Kim reports a wireless piezoresistive string sensor made of silver nanowire, which is embedded in silicone lens. And it has got a chip and an antenna for wireless transmission of data. How cool is this? But I'm wondering, what's the weight of contact lens after embedding all these components? Silver nanowire IOP sensor has a diameter of around 12 mm, and through cast molding it was embedded in contact lens. So the overall diameter of the smart eye contact lens is 14 mm, and its thickness is 300 microns, with 91% transmittance in visible light range. Scientists have used nanofabrication technique to design this smart contact lens, and so far it has been tested on rabbits. Amazing, right? This was all about today's podcast, and if you are tech savvy and want to stay updated with trending research, do not forget to subscribe Studio Mac and make sure you like and share it. Till next episode, goodbye. Take very good care of yourself and those around you.